Hello, everyone. My name is Liang. Oh, sorry. I'm going to talk about our work. A functional workspace optimization where learning personal preference from virtual experiences. Firstly, I have a question. Did you ever have such experiences that when you tried to get something in the kitchen, you had to take off the shoes and climb up to get the items you wanted? It happened to me sometimes. And or when you prepared a meal, you have to carry a very heavy pan, traveled a long distance from the sink to the oven. Why does it happen? We all know that as a workspace, functionality is one of the most important properties, which a designer should consider. Some rules derived from population statistics are usually incorporated by designers, but users' preferences affect the functionality serving. For example, when people might prefer to place a tea table on the left of a sofa in the living room instead of on the right, I think maybe both arrangements are reasonable, but the person's experiences are different. Someone maybe feel comfortable, but others do not. So people's preference vary from person to person. For designer, to exploit a user's preference, usually he observes or communicates with the user about his daily activities, and then the designer may summarize and adjust his initial design to adapt to a specific user. But usually, the process is time-consuming, and the effectiveness depends a lot on the experience of the designer. So, to address the problem of applying personal preferences into the functional workspace design, we propose a pipeline to learn the preferences from a user and applying it into the workspace design. Given an initial workspace, our approach aims to find an optimal configuration based on the learned user preferences. Our approach includes two stages. The first one is personal preferences learning, which models a user's preferences from her activities. And then the second is optimization, which applies the learned preferences to remodel the initial workspace. To learn the personal preferences, the user experiences initialized visual workspace by varying VR devices such as HTC Vive, and she is required to perform some tasks, some predefined tasks. During this process, all parameters are captured, and then they are used to model the personal preferences for the user. When the user performs the tasks, firstly, she will receive some instructions about the tasks. Then she is required to place all items that will be used in the tasks. At last, the user executes the task instructions step by step. We record all the parameters from the VR devices sensors, which will be used later to optimize the workspace. Here is a demonstration of how the user performs the tasks. It's worth to note on the right, the avatar is just for visualization. And the task here is to fry a steak. The preferences are reflected by the captured activities of the user. Here, we show an example of the user's captured trajectory on the right. We cluster the user's activities according to which item she interacts with. As shown in the figure, each bar with different colors depicts the component with which the user interacts with. These clustered activities encode both the preferences on the user's workflows and the preferences on objects placing. Considering the independence between the floor plan and the wall plan, we decompose the optimization into two parts. The first is floor plane optimization, which focuses on optimizing the location of each component along the floor plan. Wall plan optimization, which focuses on the height of each component. For the floor plan optimization, we define two costs here, and they are preferences cost and spatial cost. For the preference cost, we consider the traveled distance and the loads carried by the user when she moves around. And for the spatial cost, we considered accessibility term and free space term. For the accessibility cost term, which is ensure enough space for user to interact with objects. For example, a user should have enough space to open a cupboard door. The free space will try to keep as small space as possible for the user to work through. There is an example of the floor plan optimization. The curve on the right is the cost change during the optimization. On the left is the visualization of the sampled configuration for the workspace. In the wall plan optimization, we define two cost terms for the height of the components. We refer to the pose assessment score, such as a rebel score, to define the pose cost. Considering that the user wants to see the workspace with less occlusion, we define the visual field cost. Please refer to our paper for more detailed definitions. Here is an example of the wall plan optimization process. We discretized the solution space, and then exhaustive search algorithm is used to find the optimal height. In order to verify the effectiveness of our approach, we experiment on four things, and which are created based on some traditional kitchen layouts, such as L-shaped, U-shaped, or one-wall shaped. Firstly, we compared our approach with some other design approaches, such as designer approach, where the workspace is designed by a designer, and we also compared with the approach from a user. In the designer approach, the workspace was manually created by a designer who had about 3 years experience on interior design. And in the user approach, the workspace were manually created by the participants before they experienced in the virtual workspace. Both the designer approach and the user approach were allowed to adjust both layout and the height. 24 participants take part in the user study, and from the results, we can observe that both our approach and the designer approach work well. But if we consider the time, our approach took about 4 minutes to output the workspace. But for designer, it spent about 38 minutes to complete the task. We also tried to investigate if our approach have learned the personal preferences well. So we invited 10 participants to take part in this study. In this study, a user experienced all things. That means 4 things. So A and C are the activities captured by our approach, and B and D are the output results. It's interesting that we can see from the row B, the yellow object and the green object, they are optimized to keep close because the user in the experience, she always prefer to transfer from the freezer and the sink. Here, we summarize our contributions. By learning the personal preferences from human activities, we propose a pipeline to remodel a workspace. We define a cost function to model the personal preferences, including spatial constraints, post-assessment, and visual field. We conduct experiments and perceptual studies on different settings to validate the effectiveness of our approach. That's my presentation. Thanks for your attention. Thank you.
I have one question for you, to be quick. So have you considered asking participants to make their own arrangements of the furniture and then do the task once they learn about the task to make arrangements? And if that would be the case, what type of changes would you have to your algorithm?
Sorry.
So when participants come to your study and you give them tasks to do, how about asking them to rearrange furniture and make changes that they think would be best for that task?
Actually, when we did the user study, we have a user approach to compare. In the user approach, the user are allowed to set up the arrangement as they liked.
Okay, perfect. Excellent.
Okay, thank you.
All right,
Thank you so much.
very
Thank
much.
you.